Hello and welcome. In this presentation, we're going to talk about how to achieve optimal price performance per watt in FPGA design with Kintex-7 FPGAs. But first, let's give an idea of what kind of application requirements we're talking about, and hence the need for a mid-range FPGA solution. In any given general market segment, such as wired communications, wireless infrastructure, consumer, medical, and military radio, you have a wide range of solutions in any given application space. For example, wired equipment ranges from low-end access devices to very high-end core routers, and wireless infrastructure ranges from small cells to large base stations. In each of these segments, perhaps not the highest-end router or the lowest-end consumer device, you're going to have applications needing a mid-range solution with competitive price points, but still high-end performance and power efficiency. Xilinx introduced the Kintex-7 FPGA family with this in mind, delivering an ideal balance of price performance per watt for a breadth of applications, and providing features similar to those of high-end devices, such as cutting-edge transceivers and high-speed integrated IP. So in this presentation, we'll review some of these capabilities and provide application examples where the Kintex-7 family is an ideal fit. First, it's worth pointing out that the Kintex-7 and the entire 7 series is based on TSMC's high-performance, low-power, or HPL, 28-nanometer process. And there are reasons why the HPL process is the optimal choice for FPGAs. But to understand why it's such an ideal choice, it's useful to look at what the other main vendor is using for their 28-nanometer FPGAs. Their high-end family uses the 28HP, or high-performance process, which is ideal for applications like GPUs. And for their mid-range and low-end products, they chose the 28LP, or low-power process, which is best for applications like cell phones. But both processes are not ideal or power efficient when considering the operating ranges for FPGAs. On the Xilinx side, we chose to work closely with TSMC to develop one versatile 28 HPL process that has sufficient process headroom to accommodate the full range of FPGA devices, operating ranges, and applications, so we can deliver the best performance per watt. Specifically, by combining the HPL process with multiple 7 series innovations, we cut total power consumption by 50% compared to the previous generation. This provides headroom for additional performance, and we did this in multiple ways. One, we re-architected the transceivers for a significant 60% power reduction. And for I/Os, one area where the I/O historically has consumed a lot of power is in memory interfaces. So now we're saving power during memory operations by turning off, on a pin-by-pin basis, the input buffer and termination while the memory interface is in write or idle mode. For dynamic power, intelligent clock gating and refined architectural blocks reduce power by roughly 30%. And for static power, the HPL process itself has incredibly low leakage. Moreover, the headroom of the process enables what's called power binning and voltage scaling. And what we mean by that is because the process is so robust and delivers so much headroom, we've screened for parts that can operate at 2 voltages, the standard 1 volt or a lower 0.9 volt that still delivers optimal performance but at a lower power. So designers can make a choice on a design-by-design basis, even within the same part and same socket on the board if they want to scale voltage down. And there are multiple dimensions of performance when talking about the Kintex-7 price-performance watt balance. This ranges from transceivers, to memory interfaces, to I/O performance, to DSP bandwidth, to block RAM performance, and fabric speeds. The Kintex-7 is an ideal fit for a variety of applications that are dependent on any of these performance metrics. And it achieved all this by leveraging its 4th-generation column-based architecture, allowing for the ideal feature mix at the lowest price point, such as the ratio of fabric and resources such as block RAM, DSP, I/Os, and transceivers. This column-based layout eliminates constraints such as dependencies between I/O count and fabric array size, allows power and ground to be placed anywhere on the chip, and allows disparate hard IP blocks such as analog mixed signal and PCI-Express to be scaled independent of each other and surrounding resources. The broad configuration of devices, as shown in this product table, are a result of this flexible architecture. For example, critical to the resource mix is the types of I/Os and transceiver count. Different applications need different ratios. As shown in the table, the K70T, 160, 325, and 410T feature a moderate number of transceivers and high-range I/Os for applications needing the ideal price-performance balance. But the family also includes the K355T, 420, and 480T devices that favor transceivers with fewer I/Os, ideal for higher performance wireless applications, for example. So now let's take a closer look at some of the key architectural blocks. All 7 series devices are made of the same logic fabric for optimal implementation and efficient migration across families. A simplified view of a configuration logic block, or CLB, is shown in the middle of the slide here. Inside each block are 2 slices, each of which is comprised of the architecture shown at the right. Now each slice consists of 4 6-input LUTs, which is the main logic resource for combinatorial functions. It can support any function of 6 variables or 2 independent functions of 5 variables for greater flexibility. Wide multiplexers combine the outputs of 2 LUTs for larger functions, and carry chain logic implements fast arithmetic functions across slices along the vertical columns. And the 4 flip-flops are the primary storage elements that can also be configured as latches, and these registers are augmented by additional flip-flops. The Kintex-7's DSP blocks are specialized silicon that help deliver high performance and power efficiency for computationally intensive functions. They're useful for both simple arithmetic operations that you'll see in most applications and complex signal processing you'll see in applications like wireless, imaging, and broadcast. In fact, the Kintex-7 has the highest DSP to logic ratio in its class and in the 7 series to make it ideal for such markets. Each multiplier supports 25 by 18 bits and can be cascaded with another slice via 5 high-speed interconnects to make up a tile to implement up to 35 by 24 multiply operations in a DSP tile with a pre-add block, and 35 by 26 multiply operations without a pre-add block. Now the multiply and accumulate resources can be accessed separately for efficient use of the slice, meaning users can select different arithmetic operations on a clock-by-clock basis. Looking at the transceivers, these operate at line rates of 12.5 gigabits per second and are ideal for cost-effective backplane and optical applications. The GTX transceivers, as they're called, provide the lowest jitter in their class and wide-range tuning capabilities. In fact, because they cover such a broad range of applications, the PLLs driving the transceivers are based on both ring-based and LC tank oscillators for the highest flexibility. And at these line rates, because serial link simulation before going into hardware is so important, the GTX transceiver has an IBIS model kit to enable fast and accurate simulation to estimate performance. Also critical is capturing results in real hardware. The transceiver provides an on-chip scope, known as 2D iScan, that helps determine link margin without the use of expensive test equipment. And the GTX transceiver provides the industry's leading adaptive equalization solution to compensate for signal distortion. This includes pre-emphasis, continuous time linear equalization, and decision feedback equalization, or DFE. Now this is an incredibly important feature for backplane applications operating at 10G or above. In fact, for such applications, multiple equalization techniques are critical to compensate for signal distortion across a long transmission channel. Each technique offers multiple settings to handle different conditions, and the matrix of settings can easily go to thousands or millions of combinations. Manually selecting the optimal setting from so many combinations is tedious and error-prone. This is where Xilinx's auto-adaptive equalization is critical, and a backplane with multiple line card slots is a good example to illustrate this. The channel condition will vary if the line card plugs into different slots or if there's significant variation in voltage or temperature. Usually, different equalization settings must be applied for different slots since the transmission channel changes in length. Now in manual mode, this is difficult, as we discussed, but with Xilinx's auto-adaptive equalization, the transceivers recalibrate automatically if the line card is moved. Now looking at PCI-Express, the Kintex-7 provides a feature-rich and high-performance PCI-Express solution. It has an integrated PCI-Express Gen 2 hard block and a soft IP implementation supporting Gen 3. With the ability to be configured with easy-to-use GUI tools, the bandwidth is scalable up to 8 lanes and easily supports Gen 1, Gen 2, and Gen 3 data rates. The block supports both endpoint and root port using the AXI interface, and advanced error reporting provides more granularity and control for the types of errors that can occur in a PCI-Express system. The integrated block also optionally performs automatic end-to-end CRC checking and generation. Reference designs and evaluation kits are actually available, as will be shown at the end of the presentation. The Kintex-7 memory interface operates at up to 1866 megabits per second in a mid-speed grade, which translates into a high-performance, cost-effective solution. It offers broad protocol support, including DDR3, DDR3L, and RLDRAM3, among others. Now, in many designs, the architecture of both memory controller and interface can determine the performance of the overall system. With the 7 series, Xilinx took an approach where we decoupled the PHY layer from what is now a soft memory controller. This allows designers to customize the controller using an easy-to-use memory interface generator, or MIG. In fact, there is a tutorial on using the MIG with Vivado that's available on the sidebar of your screen. Now, the challenge becomes how to keep up with DDR3 data rates using a controller based on logic fabric. The improved PHY architecture makes this possible with a dedicated FIFO, as shown in the graphic, that provides the gearbox capability to decouple the memory clock rate from the controller clock rate at just the right ratio. So now that we've gone through some of the key architectural blocks, let's look at some real-world applications. Wireless infrastructure must support numerous standards, like GSM, WCDMA, and LTE. Now, remote radio heads are critical components for a base station. Among the key requirements in remote radio head design is DSP and transceiver bandwidth. There is a need for higher signal processing capacity and serial interface performance. And because remote radio heads are commonly installed at the top of cell towers, buildings, and other infrastructure, their size and weight and power are critical. Now, with an optimal balance of price, performance, and power, the Kintex-7 FPGA is an ideal fit. With up to 1,920 DSP slices, these devices deliver the highest GMAC processing capacity in their class. That's important for the radio's critical digital algorithms. In fact, Xilinx offers a comprehensive portfolio of IP building blocks for multi-mode radio design. And because of outdoor limitations, the low-power architecture of the Kintex-7 is welcomed where there are limiting cooling resources. Another ideal application for the Kintex-7 is software-defined radio, now a common method of military communication. These radios support video, voice, and data and are carried by foot soldiers, installed in air and ground vehicles, and located at base stations. The ability to distinguish and process signals depends heavily on the DSP processing capacity of the receiver circuit. Vehicle and airborne-based SDR systems, in particular, are typically installed in standard-sized compartments with very limited area, ventilation, and cooling resources, and that creates design challenges in terms of form factor and heat dissipation. The Kintex-7 delivers the necessary DSP bandwidth to support a continually growing number of wideband and broadband waveforms. But important is not only bandwidth, but performance per watt. Because the Kintex-7 is based on the HPL process, as performance increases, so does power efficiency over competing solutions. Additionally, because data security is often a priority in military communication systems, one common requirement is the separation of encrypted and unencrypted data in the hardware. Rather than use multiple devices, designers can leverage the Xilinx isolation design flow, which enables multiple physically isolated functions to be implemented within a single FPGA. In wireless communications and software-defined radio are only a couple of segments where the Kintex-7 is suited. Its resource balance, power efficiency, and price point make it a fit for other applications like data center, cockpit displays, and avionics, and high-resolution portable ultrasound, among others. And when talking about applications, it's important to note that this family is part of the scalable optimized architecture that makes up the 7 series. By using the HPL process and the same architectural building blocks for the Vertex 7, Kintex 7, and Arctic 7, the series provides easy design migration across families, eliminating time-consuming re-optimization if you want to move to a different target with different specs. So if you target a Kintex-7 for a portable ultrasound, for example, you have the flexibility of scaling down this design to a smaller unit or developing a more advanced system with, say, 256 channels. So if you'd like to learn more, visit the webpage at xilinx.com/Kintex-7, or you can also read the white paper or view the demos linked on the sidebar. And if you're ready to get started designing, evaluation boards are now available and can be purchased by either contacting your local representative or visiting xilinx.com/boardsandkits, both linked on the sidebar of your screen. Thank you, and hope you've enjoyed this presentation.